Hi there, Mr. Sutton here with the BC Calculus 7-8 Extra Practice number 1 solutions on interval of convergence. On this problem, we want the radius of convergence. So the key on this is recognizing we have a geometric series. We just have an r value of x that we're multiplying by over and over again. So to get the radius of convergence, we take our common ratio, which is x, take the absolute value of that and set it less than 1. And if we're in 1x minus a form, then whatever's on the other side is the radius of convergence. So in this case, the radius of convergence is just 1. We're going to be finding the radius of convergence for this series here. To make our lives a little bit easier, I'm going to combine this n and this square root of n. This is really n to the first times n to the 1/2, or n to the 3/2. So that'll just give me fewer n's floating around for my next step. Now, I notice that this is not a geometric series. It's close. We have an x to the n and a 3 to the n, but this non-nth power is messing us up. So we're going to use the ratio test to figure out radius of convergence on this. So I'm going to have the limit as n approaches infinity of a big fraction, and at the top of the fraction I'm going to have the n plus 1th version of this divided by the nth version of this. So n plus 1th term, that's going to be x to the n plus 1, n plus 1 to the 3/2, 3 to the n plus 1, all in their own fraction up here. And we're dividing all that by the nth term, which is essentially just the summand here. Same change flip. In my numerator, I'm going to have the x to the n plus 1, and this 3 to the n to the 3/2 is also coming upstairs to be with the x to the n plus 1. Downstairs, we have all of this stuff here, times the x to the n. And now it's time to reduce this a little bit to make my next step easier. So we have a 3 to the n, 3 to the n plus 1. That reduces to just a 3 in the denominator. So this 3 up here is gone. The n's to the 3/2, those are going to stick around for one more step. With these x's, this reduces to just an x in the numerator. So in the numerator, all I have left is n to the 3/2 and an x. In the denominator, I have a 3 left over and an n plus 1 to the 3/2. So if I were to multiply all this out, we end up having an n to the 3/2 and essentially a 3n to the 3/2. As n approaches infinity, we can forget about this little plus 1 in here. So we really just have n over 3n, or n to the 3/2 over 3n to the 3/2. That reduces to 1 over 3. And then we still have this x hanging around, which gets treated as a constant. So we have the absolute value of 1 over 3x. And now for radius of convergence, I'm going to take this and set this less than 1. Now I need to put this in 1x minus a form to get the r on the other side of the absolute value inequality. So I'm just going to multiply both sides by 3. So we have x is less than 3. And now since I have 1a or 1x minus a form on the left side, whatever's on the other side is my radius of convergence, which in this case is just 3. On this one, we want the radius of convergence for this series. Now there's a couple ways to do this one. It would probably be possible to do this one as a geometric series if we take out one of these x minus radical 2's and then say we have a common ratio of x minus 2 radical 2 squared over 2. But if you weren't sure about that, you could use the ratio test on this. So limit as n approaches infinity of the n plus 1th term, which is going to be x minus root 2, 2 times n plus 1 over 2 to the n plus 1, so all of this craziness. And we're dividing all that by the nth term, which is just what you see up here. Same change flip, and I'm going to reduce, or I'm going to simplify this a little bit. So in the numerator, I've got x minus radical 2 to the, let's see, this is going to be 2n plus 3 if I distribute that out. I'm also going to have a 2 to the n up there as well. And now in the denominator, I've got this 2 to the n plus 1, and also this 1, or x minus radical 2, 2n plus 1. Reducing things a little bit, and here's where you see that this really was a geometric function because you've got all exponential terms here. We're going to have a 2 left over in the denominator, and subtracting these exponents, we're going to have an x minus radical 2 squared in the numerator. So there's that. There's the 2 in the denominator. we're going to set this less than 1. And now to actually find the radius of convergence, I need to get this in 1x minus a form. So this square's got to go. This divided by 2 has got to go. We'll take care of this 2 down here first by multiplying both sides by that. Next, I have to unsquare this side on the left here. So I'm going to just square root both sides. That's going to give me the square root of 2 on the right side. And now I've got this in 1x minus a form inside the absolute value. So whatever's on the other side here is my radius of convergence, which is just radical 2. To find the interval of convergence on this one, I'm going to first check to see if it's a geometric series. It looks like it is. I'm just multiplying by negative 4x plus 1 inside of parentheses every single time here. So that's my common ratio that I can put inside an absolute value and set less than 1. So I'll say just absolute value 4x plus 1 is less than 1. I can ditch the minus because I've got an absolute value to help me here. So I have to get this in 1x minus a form to get, well, actually I don't even need to do that, right? I just need to actually solve this for x. I was thinking radius of convergence, but we want interval of convergence. So let me go ahead and just say negative 1 less than 4x plus 1 less than 1. And now solving for x, I'm going to subtract 1 from everywhere. So this is a negative 2, this is a 4x inside, this is a 0 on the other side. Dividing everything by 4 now to get x completely by itself, we have negative 1/2 less than x less than 0. And since this was a geometric test that we essentially did to find our interval of convergence, we're guaranteed that our function is not going to converge at these endpoints here. We're guaranteed these are just less thans, not less than or equal tos. There's no ambiguity for the geometric test. So this is our interval of convergence, and we don't have to do any further testing. For this problem, we want the interval of convergence for this series. Since this is not a geometric series because of this n plus 1 messing things up over here, I need to use my ratio test to find this. So I'm going to have limit as n approaches infinity of the n plus 1th term. So that's going to be n plus 1, which is actually n plus 2, times x to the 3 parentheses n plus 1. So that's my n plus 1th term, divided by the nth term, which is just what you see here inside the sigma expression. And now I can reduce this a little bit with these exponents. So this is really x to the 3n plus 3. If I subtract 3n from that, then I really just have x to the 3rd in the numerator. And in the denominator, I just have n plus 1 left over. Now, as n approaches infinity, we can ignore the little plus 2 that's next to the n here, and also the plus 1. Those basically don't make a difference if n is approaching infinity. So we really just have n over n with a coefficient up here of x cubed. That's just going to be x cubed because those n's basically cancel each other out. So we have absolute value of x cubed, which we're going to set less than 1. So for our interval of convergence, we need to get x isolated. I can actually cube root both sides right away. So I can just write absolute value of x is less than the cube root of 1, which is also 1. And now I can say negative 1 less than x less than 1 to get rid of the absolute value. But because I used the ratio test and not the geometric test to get this, I don't know for sure whether or not I converge at these endpoints of negative 1 and positive 1. That's why I've got this question mark here. So I now need to test each endpoint to see if it individually makes this series converge. So testing out the endpoint at x equals negative 1 first. If I plug negative 1 in here for x, then I've got, this is going to be negative 1 to the 3n, which is essentially going to be alternating back and forth depending on whether n is even or odd. So we've got n plus 1 times, this is essentially the same as negative 1 to the nth power in terms of what it's doing. As n approaches infinity for this, I'm going to run the nth term test. As n approaches infinity here, we're growing larger and larger and then flipping back and forth. So this is like plus or minus infinity, not 0. So this is going to diverge by the nth term test, and this negative 1 has just less than, not less than or equals to. All right, let's plug in positive 1 for x now. If we do that, then 1 to the 3n is just going to be 1, which is just going to go away. So you essentially just have n plus 1 for your series. And if we try the nth term test on that, that's a pretty easy one to run. The limit of this is just going to be infinity, which again is not 0. So this also fails the nth term test. Since this diverges, our true interval of convergence is just what we started with here, -1 less than x less than 1. For this problem, we want interval of convergence for this series. Now, at first glance, this looks kind of geometric because we have the nth power for both of these. But if you rewrote this as x over n to the nth, you wouldn't really be multiplying by the same thing every time you increase the value of n, because the stuff inside that fraction would be changing at the same time as your exponent. So we're going to have to use ratio test here. We'll have the n plus 1th term, so x to the n plus 1 over n plus 1 to the n plus 1. And we have a limit as n approaches infinity for this huge fraction here. So we're dividing the n plus 1th term by the nth term up here. Same change flip. We've got x to the n plus 1 times n to the n over n plus 1 to the n plus 1 times x to the n. We can reduce this a little bit. These x's, if I subtract the exponents, we just have an x upstairs to be with that n to the n. Still have n plus 1 to the n plus 1 downstairs. Now, as n approaches infinity, this plus 1 is going away, so you essentially just have n to the n over n to the n plus 1, which reduces to just, we just have really x over n. But as n approaches infinity, since that's bottom heavy, that's going to zero out. And since this is already less than 1, I mean, we're going to set this less than 1, but since 0 is less than 1 for all values of x here, this actually passes the ratio test, converges for all x values, which means our interval of convergence is just going to be all real numbers, negative infinity, less than x, less than positive infinity. To find the interval of convergence on this one, let's first check to see if we have a geometric series. Turns out we do. We're multiplying by negative parentheses 3x plus 6 every single time. That's our common ratio. So this is a much quicker process than using the ratio test. We can just take the absolute value of this and set it less than 1. Since I've got absolute value going on, I can forget about this negative out in front. So I really just have absolute value of 3x plus 6 less than 1. And to get the interval of convergence now, I just need to solve for x. So I'm going to rewrite this as -1 less than 3x plus 6 less than positive 1. Let me subtract 6 everywhere. So this will be -7 less than 3x less than -5. And now dividing by 3 to isolate x, I have -7/3 less than x less than -5/3. And this will be my interval of convergence. Now, since I did this with the geometric series and I didn't use the ratio test, that means I know for certain that this is my interval of convergence. I don't have to test the endpoints, so I'm done. For this problem, we want the interval of convergence for this series. The key on this one is recognizing that we have a geometric series. We're multiplying by a common ratio of 2/3 x minus 1 every single time. So let me just put this inside an absolute value, set it less than 1, and that'll give me my interval of convergence. So to get the interval of convergence, let me make my life a little bit easier because I'm going to be solving for x here. I'm going to multiply both sides by 3 over 2. So that'll give me just x minus 1 inside absolute value less than 3/2. And now I'm going to rewrite this with my double inequality. So -3/2 less than x minus 1 less than positive 3/2. And let me just add 1 everywhere to get x by itself. So -3/2 plus 1 is -1/2 less than x less than 5/2. Since I got this with the geometric series test, I know that this is my interval of convergence now. I don't have to test the endpoints like I would have had to do with the ratio test. So I'm calling this one done. For this no calculator free response, we have some function f with a Taylor series about x equals 2 converging to all x in the interval of convergence with an nth derivative given by this wacky factorial exponential expression. And they're also telling us f of 2 is 1. All right, so based off of all this, first task they've given us is to find the first 4 terms in general term of a Taylor series for the function about x equals 2. So we've got everything we need to write this out. They gave us all the derivatives here, basically, at x equals 2. We just have to plug in different values of n to get those. I'm going to write out my general kind of formula for a Taylor series about 2, and then I'm going to start plugging things in. So my general series is going to have the form of f of 2 plus f prime of 2 times x minus 2 plus f double prime of 2 over 2 factorial x minus 2 squared. And then they wanted the first 4 terms, so I'll do one more. F triple prime of 2 x minus 2 cubed over 3 factorial. They also want the general term, so that's going to be essentially this, f of the nth derivative of 2 times x minus 2 to the n over n factorial. So now I'm actually going to plug some things in. So f of 2, they actually told us that. That's 1. F prime of 2, we can figure that out based off of this. So that's going to be plugging in 1 for n. So that would be 1 plus 1 factorial, which is 2, over 3 to the 1 power. So 2/3 basically times x minus 2. And then I'll just leave the factorial there for now. And then for the next one, we're plugging in 2 for n for that nth derivative. So that's going to be 3 factorial over 3 squared times x minus 2 squared. And then we have a 2 factorial down there as well. Don't forget about that. That's why I actually wrote out this form first, so I don't forget those factorials that already come with any Taylor series. And then for the next one, third derivative, that's going to be, let's see, 4th factorial upstairs. We've got a 3 to the 3 and also a 3 factorial in the denominator and an x minus 2 cubed. So a lot of stuff going on in these. And then for the nth derivative, nothing terribly special going on. We can just write this expression. So we're going to have n plus 1 factorial, x minus 2 to the n, and we're also going to have a 3 to the n and an n factorial downstairs. Now, I actually already have this in polynomial form. These x minus 2's with an exponent are okay. The coefficients don't have to be simplified, so if I really wanted to, I could leave it like this. But I have a sneaking suspicion I might need this simplified for later on in the problem. So I'm going to go ahead and simplify this. Now, if this were the real AP test, I would wait until I actually needed to simplify it. But we're here now. I'm not actually taking the AP test at this moment in time. So I'm going to simplify these right away. So I've got 1, and this is going to be just 2/3 x minus 2. This is going to be, let's see here, 3 factorial over 2 factorial. Gets rid of all the factorials except for that 3 at the beginning. So we have a 3 over 3 squared, which reduces to just 1/3 x minus 2 squared, which looks a lot nicer than this, right? And then we have 4 factorial over 3 factorial is just 4 up here. We have a 27 downstairs, so 4/27 x minus 2 cubed. And I'll go ahead and actually take care of this one too. I'd like to get that general term looking a little nicer. N plus 1 factorial over n factorial is just n plus 1. And we still have a 3 to the n downstairs with an x minus 2 to the n upstairs. So there we go. For this next problem part, we want the radius of convergence for the series we just wrote. So here's the general term again that we got from part A, n plus 1 over 3 to the n, x minus 2 to the n. So we're going to use the ratio test on this to find the radius of convergence. We can't use the geometric test because this is not actually a geometric series. This n plus 1 term is messing us up. So let me do the n plus 1th version of all this over the nth term, and we'll do the limit as n approaches infinity for all this now. This is just our ratio test. So n plus 1th term, what does that look like? Well, we have n plus 1 plus 1, so that's really n plus 2. We have a 3 to the n plus 1, and we have an x minus 2 to the n plus 1. So all of that is our n plus 1th term. Nth term is just this right here, so we'll put that downstairs. Same change flip. We've got n plus 2, x minus 2 to the n plus 1, times 3 to the n upstairs. Downstairs, we have 3 to the n plus 1, n plus 1, x minus 2 to the n. We can reduce this a little bit to make the next step easier. These 3's reduce to just give me a 3 in the denominator. These x minus 2's are going to reduce to give me an x minus 2 in the numerator. So upstairs, I've got an n plus 2 and an x minus 2, and that's it. Downstairs, I still have a 3 and an n plus 1, and that's it down there. So now as n approaches infinity, this plus 2 and this plus 1 next to the n's go away. You essentially have n over 3n, which is 1/3. You still have this coefficient of x minus 2 hanging around. So x minus 2 over 3 then. Since we want to find the radius of convergence, we're going to set that less than 1. And to get the real radius of convergence, I have to put this in 1x minus a form. So I can't have this 3 hanging around. I'm going to multiply both sides by 3, giving me 3 on the right side. Now I've got 1x minus a form. So whatever's on the other side of this inequality is my radius of convergence, which is going to be 3 in this case. On this problem part, they're telling us g is a function such that g of 2 is 3, and g prime is really f. We want the first 4 terms in general term of a Taylor series for g about x equals 2. Okay, so let me write out a general Taylor formula about x equals 2, and then I'll start plugging things in. So I can say that I need g of 2 plus g prime of 2 times x minus 2 plus g double prime of 2, x minus 2 squared over 2 factorial. So we already did this kind of for the f function, and then I need one more here. So g triple prime of 2, x minus 2 cubed over 3 factorial, and the general term, nth derivative of g at 2, nth factorial, x minus 2 to the nth power, and so on and so forth. All right, so let me start plugging some things in. So I know that g of 2 is really 3. G prime of 2, we're really asking for f of 2 times x minus 2. So I'm just going to write f of 2 here. And then I'll do one more layer of plugging things in. This is really going to be then f prime of 2, x minus 2 squared over 2 factorial, f double prime of 2, x minus 2 cubed over 3 factorial. And this is going to be the, let's see, this would be the n minus 1th derivative of f at 2, x minus 2 to the n over n factorial. So that's where we stand if we apply the fact that g prime and f are the same thing. So now we actually have to go and get some constants for all this. So let's see, we still have a 3 here. F of 2, they already told us that way before. That was 1. So this is really 1 times x minus 2. So we've already got the first 2 terms. This is great. F prime of 2, well, here's what f prime is doing, or f, the nth derivative of f at 2. So this is the first derivative now, so this is going to be 2 factorial over 3 to the first power. And we've got a 2 factorial downstairs as well. And then we've got an x minus 2 squared. Next, second derivative of f, that's going to be 3 factorial upstairs, 3 to the second, and 3 factorial downstairs. And finally, for the nth term, that's going to be, let's see, this is n minus 1 plus 1. So this is really n factorial up here, 3 to the n minus 1, and n factorial downstairs with an x minus 2 to the n upstairs. If we wanted to, we could go ahead and simplify this as well. So that should come out to 3 plus x minus 2. 2 factorials cancel. This is just 1/3 x minus 2 squared. 3 factorials cancel. This is 1 over 3 squared x minus 2 cubed. And you could call that a 9 if you wanted, but it's really 3 squared. Over here, for the general term, nth factorials cancel. So this is really 1 over 3 to the n minus 1, x minus 2. And this actually should be the nth power here. Let me fix that. There we go. That's a little bit better. So yeah, this is then going to be 1 over 3 to the n minus 1, x minus 2 to the nth power. For this last problem part, they want to know if the series for g that we did in part C, and here it is again for our reference, converges at x equals negative 2. And then give a reason for the answer. So there's a few ways to do this. Most straightforward is going to be to figure out the interval of convergence for this thing, and then see if negative 2 falls in that interval of convergence or not. So interval of convergence on this one actually isn't so bad, because there's a pattern here if you actually took the time to simplify your series from part C. We've got, let's see here, x minus 2, And then this is 1/3 x minus 2 squared, 1/9 x minus 2 cubed. So we're multiplying by 1/3 x minus 2 each time. So that's our common ratio. And this actually turns out to be a geometric series. So this is going to be, again, 1/3 x minus 2 is our common ratio. To get the interval of convergence, we just need the absolute value of this and set it less than 1. So let me go ahead and solve for x now. I can make my life a little easier by multiplying by 3. So I've got x minus 2 in absolute value less than 3. And then I'm going to rewrite this with inequalities. So I can write -3 less than x minus 2 less than 3. Isolating x, I'm going to add 2 everywhere. So I've got -1 less than x less than 5. And now let's take a step back because we wanted to know if our series was going to converge at x equals -2. Well, -2 is not between -1 and 5. It's outside our interval of convergence. Since it's outside, we can say for certain that our series will not converge at x equals -2. It will diverge.